Hello and welcome. So this is LC3 assembly rating strings. So this video will cover I/O and some data representation and encoding material. Right off the bat, we have essentially a task, which is how do we do I/O? And in certain languages, there's these philosophies like clean has the uniqueness type, Haskell has the I/O monad. In assembly, we don't get any of that. All I/O is done through traps. Essentially, get C is one of the traps that is in LC3, which reads a value which is interpreted as ASCII and stores that into register 0. So when I say reads a value as ASCII, I mean whatever the user types, it's going to be understood as ASCII, and whatever value ASCII has assigned will be the numerical number stored inside the register. Without, it's similar, which is you're still working in ASCII, however you're writing to the console, and it writes out with whatever is in register 0. So right off the bat, we need a prompt for input. So what do we need to prompt for input? There's multiple ways to do this, but we want to do this with the least amount of effort. So the way to do that would be realizing you need a prompt string, right? You need a string to say, hey, enter input, and a way to print that string, which shouldn't be too hard, right? You mean there in like C, that's just one line. It's printf. In assembly, it's slightly more long. However, we can make the assembler do a lot of the heavy lifting. So in C, the strings they're called C strings, which are 0 terminated. Essentially, there's things like Pascal strings, which are slightly different. But never mind that. In assembly, we're going to use the sudo op string z, which will create a 0 terminated string somewhere in memory. So you don't know the exact location in memory until the thing has actually been assembled, in which case there'll be a symbol file, in which case you would actually find where in memory the string lives. And then there's a trap instruction called puts, which essentially goes to a address. So the starting address of a string. So say you put the first character of address at memory location 3100 hexadecimal. If you said, okay, here's this address, puts, go ahead and read it. It takes the address which you stored into R0 to get this done, and it'll start printing out characters, interpreting them as ASCII until you hit the null terminator, which is just all zeros. Which makes sense because in ASCII, if you type in 0, the machine actually reads that as hexadecimal 30. So consider the following scenario, right? The instructions get, see, and out are placed in that order. If the user enters hello world, what will be displayed? You can go in and actually write the code, or you could just think about it for a moment and realize what exactly you're doing here. There's no prompt, there's nothing like that. It's just get, see, and out. That's all that's living in your assembly program currently. So with that in mind still, you can kind of read it sort of as a function call. Get C says, okay, go to input, grab the first letter, right? Because it only grabs a character. And you're grabbing H of hello world. And then you're saying, okay, we'll store it into register 0, which it is. And then the out, which is a trap call as well, says, okay, whatever's in register 0, print it out. And it only prints out one character. That works great, except there's something wrong with this. We want hello world, not just H. So the way to do that would be getting a loop. And a loop would say, okay, we have these set of instructions, and we want these instructions, when they hit a special condition of some sort, to do something, right? So you have to think about, it's sequential until you need some conditional branching. So we're going to need a loop. So if you do create a loop, how do we stop the loop? But first, let's go ahead and hop into the editor here. And I just realized I'm doing this in a thing where font size isn't really proper. Okay. Just a moment. All right. I switched terminals. Forgot about that. Okay, so we're now in the IDE. So all programs start with an origin directive, which is essentially saying where to load our program into memory. We load our program into memory at 3000 hexadecimal. All programs need to be able to tell the assembler, hey, we want to stop reading our source code, right? Our source code ends here, which is filled in by the .end directive, or sudo up, or whatever they call it. Yeah, it's a sudo up because it starts with a dot. All right, so we've done that, and we want to get user input, right? So let's go ahead with what we know, and that's get C and out. And let's assemble this. And let's simulate this. And you can see I have pressed D and then a legal instruction, and that's it. This is due to not having a halt, which is just a trap call to say stop the machine. Otherwise, it just continues down memory until it just runs into something it doesn't understand, which triggers the legal instruction. On some machines, it's not called an illegal instruction, it's just called a segfault. So there's that. So let's move this down out of the way. We won't use subroutines, so we'll just do everything inside, but you should definitely try using subroutines, because that makes your code go from spaghetti code to actually nice and clean and neat code. But that's beside the point. So we know we're getting one character and printing it out. That's it. And as you saw, it only took D, which was it. It didn't go past that. So we want to get more than that. So how do we do that? So we go back to this. We can see, well, that's slightly above that. So we can get a character, output a character, and then we just need a loop. So in assembly, you can define symbols, and we'll just say colons are allowed, but they are not required for symbols. But you can have them if you want. And essentially, so we can define a symbol here, put code inside of it. This is a subroutine now, or a function. You can think functions and subroutines are almost similar, except technically a function is a mapping from X to Y, meanwhile a subroutine is just a grouping of tasks. So we can say branch, right? So once you've gotten a character and you've printed it out, branch back, right, to this to these sets of tasks. And this is a unconditional branch, meaning it's always going to run no matter what you do, which can be a bad thing or a good thing. And I'll show you why. So we're going to have to assemble this again. And then we're going to simulate this. And we're going to say test, 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 test. And enter doesn't do anything, it just runs forever. So that was an infinite loop. But here's something that's slightly interesting. If we remove out, right, if we say, okay, comment out, and we assemble this, and we run this, say test, 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 and I'm actually typing stuff, you just don't see it moving, because you haven't defined that once you press a key, that it actually gets printed out. So there's no feedback that the user sees anything going in, but there's stuff actually going in. So if you actually opened up the simulator, you'd see stuff going through. So we've gotten an infinite loop that takes input and prints it out to the console. That's great. So we want to stop the loop, right? And the way we can do that is by branch instructions. And branch instructions use something called the conditional code, which is set by specific instructions like add and other ones that I can't currently remember. So essentially we can use the fact of that, let's go to the next slide. So we can use the fact that we have this, which says, okay, well, I'm not sure which of these slides would be better to look at, so we're just going to go on to the next one, which explains why they both use 000A, or just 10 decimal. So when you type in stuff to the simulator, it interprets it all as ASCII. ASCII defines characters for the values between 0 to 127, which can be represented in 7 bits. So 2 to the power of 7 is enough to fit all these things. However, because of just performance reasons and just simplicity's sake, generally 2 to the power of 8 is used. Should I say performance reasons? I should probably have said efficiency, because there's a parity bit for ASCII and whatnot. So in ASCII, A, hexadecimal, is mapped to the control character J, which has a symbol or notation of that as seen on the slide. So the control character means line feed, and line feed is different than carriage return. And what that actually means refers to teletype systems, which is beyond this. However, if you want to find a nice piece of history, just look up teletype systems and you'll understand what's the difference between a line feed and a carriage return and why you needed both back then. And how about now? It's, well, Windows still uses carriage return line feed, which is not what we use on Unix or Linux or Unix-like systems. Unix-like systems just use \n, which is just the default control character on the system. However, there's a caveat to this. When you hit enter, the operating system determines what is sent to the program. However, the program can also determine how to interpret this. So if you compile, say on Windows, they can automatically understand that \r/n is actually just a new line, and it won't mess with the LC3 simulator because they'll define it to like hide the carriage return. However, on Linux that's not a problem, but that's how it is. So now going back to this, we can say, okay, well, we're in our subroutine now, get user input. We're getting a character. And before we print it out, right, we want to know if it's a line feed, an enter. And if it is an enter, I'll say we got 0, which is quit. Otherwise, we want to loop back and get more data until the user actually hits enter. And that seems fair, and it makes sense. So let's go ahead and implement that. So after getting a character, we want to immediately test what it is, because we don't want to just print it out. Otherwise, you will also print out the line feed if you don't put the check before out. So in this case, we're going to say add R5, and I use R5 simply because I know it's a register that's not being used for anything special like R7 or R0. And I say R0, and I want to subtract, so I can say, okay, subtract A, which is the hexadecimal A, which is equivalent to just decimal -10. So currently this is just subtracting and doing nothing. It still do the same thing in infinite loop. So we now want to use the branch instruction, branch if 0, right? And we want to branch somewhere else. So where do we want to branch to? That's up to you. In this case, we'll make a subroutine, and I'll call it, oh, they've hit enter, so we want to now, so after getting the input, that's funny. I almost forgot. I've gone too far before actually explaining. We need a way to print the prompt string, and we need a prompt string. That's humorous. Okay, clearly, lack of sleep. So we're defining a prompt string here, and we're just saying, we'll call it, what's it? Please enter a string to echo, right? That seems like a fair prompt string. And we need to define a variable name for our symbol. And in this case, we'll just call it prompt string. So now each time when you refer to your code in this, it'll refer to the starting address, or it'll refer to this. I shouldn't say starting address, because your starting address or of the string is, you actually have to find it at runtime. So at runtime, to find the address of something like that, you can use an instruction called LEA, which is load effective address. So LEA, what? Oh no, did I switch? Okay, whoops, I accidentally had switched to different keyboards. That's not right. So let's take a look at appendix A. Alright, we want to load the address into R0 because our next instruction puts will actually get the address from R0. And we say load the effective address of the prompt string, right? So this will get us the address of please enter a string to echo, the starting address. So the very first character P will be loaded into R0. Not the character, but the address of that character. And then we'll say, okay, print that string out to the screen. And that's all to it for prompting. Right? And the symbol's, plain as is. You know what it means. So once you've gotten all this stuff right here, we still haven't defined where do we branch to. So we'll just say branch to whatever. Get user input. Once we've gotten an enter, we want to store the user input. So we're going to say store user input, right? And storing user input, we'll get to in a second. So if it's not 0, right, it's not going to branch to this, right? Oops. I should just actually go ahead and do this. Yeah, that's fine. So branch if, yeah, okay. Then output makes sense. All right, okay. So we'll step through this one by one. You get a character. You check if that character is 0. Or not 0, you check if the character is enter. If it is enter, then you jump to storing the user input. Otherwise, you just print it out to the console, and then you loop back for some more. Now there's going to be a problem with this if we just branch into store user input without doing some other stuff. Oh no, there won't, because yeah, we'll show some reasoning for this. So let's go back to the slides. So storing input, we should ask ourselves where. So we want to store it at memory location 3100 hexadecimal. But before we do that, we need to ask us, what are the instructions we can use for this even? Like, is this even possible? Does 3100 even fit in the memory of the LC3? Well, the LC3 is 16 bits, with 4 bits reserved for the opcode, leaving us with 12 bits for the operand. So 2 to the power of 12 is equal to 4096, making a traditional instruction unable to load the value 3100 hexadecimal. To do this faster, if you have a calculator on hand, you can just do 2 to the power of CL log base 2 hexadecimal 3100 plus 1 to the total exponent, which would get you 14 bits, or it gets you a number large enough that would fit 3100 hexadecimal. It wouldn't get you 14 bits. To get 14 bits, you would cut off the 2 and just use what the exponent is, which would be 2 to the power of 14. So clearly it can still fit inside the LC3. So how are we going to store it in memory? Well, once we've gotten an address, all we really need is to realize a string is quite similar to a list of characters. In fact, in some languages, a string is just a fancy way to say I have a list of characters. Though that's not actually how they're implemented in a lot of languages. There's performance optimizations done. So, for example, in Haskell, there is a library called bytestring. This is due to the normal string, which has a linked list implementation of a string, which means each character has a link to the, has a node which has a link to another node, and so on and so forth, is actually very inefficient memory-wise and performance-wise. So they have a library which is called bytestring, which completely forgets this analogy. But for now, we could think of memory like an array or a list, and we can insert values. So our hello world will have an assignment in memory. In this case, the starting and the pointer is at 100. So that means, okay, we have letter H, where our pointer is pointing to letter H, which is 100. Then we increment the pointer, and now it's pointing to letter E. So we'll continue this, right, as long as we need it, right? And we stop based on the null terminator, which is just 0, the raw machine 0. So right off the bat, we can tell we need a couple things. We're going to need a string. We need a string pointer, and we can use the .fill instruction and say, hey, the string pointer starts at 3100 hexadecimal. And we could say the string head. So the reason why we need a string head and a string pointer is because the pointer is incremented, right? So we don't always know where the string head will be. Even though we do, because it's going to be at 3100, we can't type that in manually up here due to how large the number is. So another 3100 hexadecimal. So that's all the variables we will essentially need. Now it just comes to working it in. So to store user input, we are branching right off to, okay, we got an enter, we want to stop, we've gotten all our letters. Though that's not necessarily true, because the way you have to think about it is, we haven't gotten all our letters, we've gotten some letters, which were just immediately discarded because it's R0, and R0 wasn't saved anywhere. Alright, so, because I'm doing this in real time, this makes me wonder how we should properly implement this and I don't have my own code on hand. Well, clearly we don't want to branch on 0 to start storing user input. We want to start storing user input actually before, so we can actually hold something. Right. Okay. So we're going to need a subroutine. Okay, I may have done something that I didn't want to have done. Oh, well, there's already a subroutine, so live with it. So you can branch of 0. So the user input is done, right? So that's where we're going to echo it out, print it out to the console. If it's not printing out to the console, we want to immediately go ahead and store it. So you can use something called JSR, which just calls a subroutine and then returns back to wherever we were. So it's going to always go to this subroutine, but after that subroutine finishes, it's always going to come back. So we can just say store, right? Looks good. Store it to the user input. Once that instruction finishes, come back up, print it out, then branch, get more input. Then, yep, that looks looks fine. My bad. So storing that user input. First, we want to clear. Do we want to clear? Yeah, let's go ahead and clear, because I can't remember if it's going to affect it or not. So we're going to go ahead and clear R5, because that's the register I'm always using to store and hold data. So anding something with itself doesn't clear it, does it? So yeah, that doesn't clear it, but it does do this. So if you and something with 0, that definitely clears it. So we are now, right? Okay. All right. So yeah, that does seem to work, right? So if we are storing the string, we want to load in our pointer. So we're going to say load R5, and we're going to load our pointer into there. So we're not using load effective address. So we don't want to load the effective address of where our variable is. We want the value of what is in that address. So it's going to go to the symbol table, grab it, and well, it's not going to go to the symbol table, but you get the point. It's going to use the symbol table, at least assembler will, and so on and so forth, to do this for us. So rather than actually have to hard code the values. So load R5 with user string pointer. Did I name it user string pointer or just name it string pointer? Yeah, okay. Thinking back to how I wrote it previously. So, oops. Load R5. Okay, so now we want to store whatever is in R0. So this, because we are jumping, or not jumping, we are here, we have stored, or getC stores the character that the user inputted into R0. So we want to say, hey, take what's in R0 and shove that into user, not user again, string pointer. And so the address of whatever is, not the address, but the value of string pointer, right, which is technically 3100 right now. It's saying, okay, go to R0 and at the memory location 3100 hexadecimal, store the, whatever the value of R0 is into. Store the value of R0 and whatever into, well, my goodness, English. Store the value of R0 into the memory location of 3100 hexadecimal. Wow, English. So right. Okay. So we've stored it. Now what do we want to do? We want to increment. So that's what I have this up there for. So we also have the value of the string pointer in R5. So now we can say to R5, okay, buddy, what we want you to do is we want to say, wait, do we want to say that? Yeah, we do want to say that. We want to say, okay, you are 5. Take yourself and add 1 to yourself. So this is back to the slide of where we have the pointer at 100, and then we want to move the pointer up ahead. So we're adding 1 to R5, which is the string pointer plus 1 stored back into R5. Then we want to say, okay, now we want to say store R5, excuse me, into string pointer. And that looks about right. So we're saying and clear that, and load it in. You don't even have to clear it, but okay, whatever. Clearly I'm doing something wrong in my head. You don't have to clear this, but I'll just leave it. Well, no, I won't. So we'll load the value of that into R5, then store the value of R0 into the location of memory, then add R5 to R5. No, add R5 to 1, then store that back into R5, then store R5 where the string pointer previously was, which is why we need the string head, so we know where the string is at all times, and then we need to return. So this ret is basically, hey, pop R7. So when you call JSR, it stores the current program counter, and when you call ret, it returns to whatever R7 is. So ret will just say, okay, go back here, and that's what's going to happen. Then you're going to have echo user input. Well, echo user input. I'm going to put this far down here so it actually will eventually hit halt. In fact, these values don't need to be they don't need to be outside of halt. They don't need, well, they do need to be outside of halt so we can have some nice code, but they don't have to. But you'll see why I want this. So I want echo user input. Wait, do I want echo? Yeah, I want echo user input. So I want echo user input defined here. Echo user input will essentially say, okay, hey buddy, load the well, that's not right. Load R0 with the address that we currently have stored inside. What do you mean? Oh, right, because I named it string here. That's not it. There we go. So load the actual value. So it's going to go to the address and then load the value there into R0, which is good for us. And then we can say, okay, print out everything, and then that's it. You should halt. So halt, no more. And that leaves us with about 32 lines of code, which probably is excessive. Let's see what we didn't have to do. We didn't have to do that comment, no spaces. A lot of this stuff could have been moved directly into, I don't know, hold on. Let's not optimize and let's see if I've actually messed anything up. So LC3, assemble gets, illegal operands for .fill. There you go. I've messed something up with how the .fill instruction works, and it's because I've done it how I do it in C. Okay, there we go. That's fixed. Honest mistake. My apologies. Gets. Alright, continue. Enter a string to echo. Hello, sir. And it prints it out. Oh, would you look at that? We actually wanted the printing. So, okay, quit. Vim. What was it? Gets assembly? Wow, I am so burnt. My apologies. This, we want up there. Right, sir. Who knows? Who knows these days? Awesome. So we can say, hello, test. And clearly I've now double messed something up. Okay, you know what? Let's list what we have going on here. P. Oh, the program counter is not where I want it. Something went wrong. Quit. I did assemble it. Okay. So let's find out where I went wrong in real time, showing my unprofessionalism. Loading the effective address, which is correct. We do want to load the effective address. Then we want to print it out. And then we're going to say, okay, get some input. Nice. Print it out. Branch to echo user input if it is. Oh, because this out thing right here, we need it before the and or the add, because add sets the CC and so does out, I guess. Welcome to living in the test. Yeah, okay, so I know what I'm talking about. Great. So there you go. That's how you do it, and it wasn't that hard, was it? It shouldn't have been. So we know how that works. We learned what we had to do. We needed to have a variable hold the address to the head of the string, and a variable to hold the pointer. Consequently, you need to increment it as we get input, otherwise we'll overwrite the same memory. And that's honestly that was it. There isn't much. I'll have another video up covering how to do this with pack strings, but pack strings is essentially shifting, in which case you can make a logical shift, which is done by, I think, logical shifting by 2, or is it just 1? It's a logical left shift. Anyway, thank you. That's all I have for this video. So, if you have any questions, talk to me, and I will help you out if you need it. Thanks, and goodbye.